Okay, so does everybody understand how we got the line through the blue observed data? It's not a perfect fit, but we eventually want to know the equation of this line. So in algebraic form, we're going to be doing y equals mx plus b. In our book form, we're going to be doing y equals alpha plus beta x, or y equals little a plus b x.
Is there a particular one we should stick to?
No.
Which one do you want to see?
Any of these two is fine. Yeah. Yeah, the algebra one isn't used a lot. So y equals alpha or a plus beta or b times x. And I'll use beta and b interchangeably in alpha and a. In the notes in section 2.4, you'll see that we've added an e. That's just an error term, or a little bit of, it allows for a random error. I just erase it to make it a little bit easier. Ultimately, we were trying to get the equation of this green line.
So if we see an e, we can just disregard it.
You just disregard it, yeah. It has its own all kinds of properties, but that's way beyond what we need to worry about. So what we want to do is calculate this equation, most importantly, the slope of this green line. This is essentially a prediction line. We can predict the average speed of cars on the road based upon the number of police officers. An average effect. It won't be exact, because nothing's exact, but it's our best guess, best prediction line. So I'm going to erase the table. Well, I actually shouldn't erase the table quite yet. I need space. The equation for the beta or the b, the slope, b or the slope, it may be a little bit hard to see in the notes. The numerator to do that is the sum of each individual value of x minus the mean of x. Multiply that by each individual value of y, which is represented y sub I, minus the mean of y. So the notation, a little bit different. X sub I is each individual observation of x, so the 3, the 1, the 4, the 5, the 7. X bar is the average of all your x values. Y sub I is each individual value of y, 64, 71, 61, 58, 56. And y bar is the average of y. That's the numerator. The denominator, what you divide it by, is the sum of each individual x value minus the mean of x, which is x bar, squared. So if you can't see the bars in the notes, it's kind of small print. That's what the equation is in your notes. This equation will get you the slope of this green line, this prediction line. All the steps on how to do this equation to get the slope are listed on page 4, beginning with step 1. We know all of our individual x's. 3 is an x sub I, 1 is an x sub I, 4 is an x sub I, and so on. We know each of our individual y's. 64, 71, 61, 58, 56. But we don't know x bar, y bar, the mean of x, and the mean of y. But we can calculate that pretty easily for each by adding up the x's and divide by the n of 5. So x bar, 3 plus 1 plus 4 plus 5 plus 7 is 4, 8, 13, 20, right? 20 divided by 5, I got an x bar of 4. So the average number of police cars in this data set of 5 is 4. So 3 plus 1 plus 4 plus 5 plus 7 divided by 5. Observations is 4. Y, the y bar, the average of the y values, add up 64 all the way through the 56. That's 310 divided by an n of 5, 62. Everybody got 62? Double check it. Yep. 62, Y bar average. The average value of Y. 62. I think they even did it in the book later in the chapter. You good on that one? Okay, so that was step one. You calculate the mean of x and y respectively, your x bar and your y bar. So what I'm going to do is I'm just going to keep that, rewrite that so I have space to do the math. And everybody, you've got the table written down. So you can reference it. I'm just running out of space. So x bar was 4, y bar was 62. So for each of your observations, keep your x's and your y's together. So, for example, you're going to take each individual x and subtract out the mean of x. So the first value of x we have in our table is 3. So that's an x sub I. 3 minus 4. That's your x sub I minus x bar.
Say that again. Where'd you get that 3 from?
So in your table, let's see if I can reproduce it. Number of police and average speed. See, I think I'll have enough room if I do it this way. 3 police cars is 64. 1 is so here's your table. There's your table. Okay. So there's your table of data surrounded in blue. The equation says take each individual x, subtract out the mean of x, and then multiply it by the difference between each individual y minus the mean of y. So for our first set of values, we have a 3 minus x bar of 4. And we're going to multiply that, so that's why I say keep it together with its corresponding values. 64 is our y sub I minus 62. So I'm going to set them all up before we do the math. The next x sub I is 1 police car. So take your 1 minus the mean of x, 1 minus 4. Now for its y, 71 minus y bar of 62. And let me know if I'm going too fast. I hope the microphone's picking up on, it should, hopefully. Next x of 4 minus the mean of x of 4. That corresponds to a y that we observed of 61 minus 62. Next, we have a value of x of 5 minus x bar of 4. Corresponds to an observed value of y of 58 minus our y bar of 62. And then finally, we have an x value of 7 minus x bar of 4. Multiply that by our y value of 56 minus the mean of y of 62. Double check that this is recording. Yes. So this is the setup for step number 2. Subtract the mean of x from each individual observation of x. Subtract the mean of y from each individual observation of y. Okay, so we've set up Step 2, go ahead and finish off step 2 by doing what's in parentheses. This ends up being 3 minus 4 is a negative 1. 64 minus 62 is 2. 1 minus 4 is a negative 3. 71 minus 62 is a 9. 4 minus 4 is 0. 61 minus 62 is a negative 1. 5 minus 4 is a 1. 58 minus 62 is a negative 4. And then finally, 7 minus 4 is 3. 56 minus 62 is a negative 6. So that would complete step 2. What we have in red. We took the differences of everything in the parentheses. Questions? Now, step 3, because the parentheses are next to each other, you multiply. So, for the first set, we have a negative 1 multiplied by 2 to start out step 3. So, a negative 1 times 2 ends up being a negative 2. The negative 3 times a 9, negative 27. 0 times a negative 1 ends up being 0. 1 times a negative 4 is a negative 4. And then our 3 multiplied by a negative 6 is a negative 18. Questions about step 3? Step 4, add them all up. So everything in blue that we've just done, negative 2 plus a negative 27 plus a 0 plus a negative 4 plus a negative 18. And that will get you that summation and get you the numerator. Yes, so we've got a bunch of negative numbers. So you see a negative 29, negative 33, negative 51. And that is what you've done to get the top value of your fraction or your numerator up there is a negative 51. So that's step 4 gets you your top number. Questions or need to see it again? Now, I usually first set it up like I did in green here because it makes going to do step 5 much easier. So step 5, we're trying to get the denominator. We take each individual x value, subtract out the mean of x, and then square it. So what I usually do is keep these numbers, because we've already done x sub I minus x bar. So what I do is then I just erase the y so I don't get confused. And you have all of your x values. 3 minus x bar, 4. 1 minus 4, 4 minus 4, 5 minus 4, 7 minus 4. Okay. And all you have to do to help with step 5 is then to square these differences. So that negative 1 gets squared. That negative 3 gets squared. The 0 gets squared. The 1 gets squared. And the 3 gets squared. Maybe time if you're rewriting it. And that satisfies what's in parentheses in the denominator, each individual x value, minus the mean of x. So we get 3 minus 4 is a negative 1. Square it is 1. 1 minus 4. So we observed 1 police car minus 4 as the mean. You get a negative 3 squared is 9. 4 minus 4 is 0 squared, which is 0. 5 minus 4 is 1, And 1 squared is 1. And 7 minus 4 is 3. 3 squared, or 3 times 3 is 9. And there's your step 5. So we've done what's in parentheses and exponentiated it. And now we just have the sigma, or the summation, for step 6. Add them all up. So 1 plus 9 plus 0 plus 1 plus 9, you have 20. And that's your denominator in your slope equation. 20. And if you divide it out, a negative 51 divided by 20, negative 2.55. That gives you beta, or b, or the slope of this green line. So the slope of this green line, negative, it's going out the negative direction. If it was a positive 2.55, it'd be going from southwest to northeast, but it's negatively sloped. And this slope is 2.55 units. So it's rise over run, or the change in y over the change in x. Y changes by negative 2.55 for each 1 unit change in x. So basically in this green line, let's go, when we go from, say, 2 police cars, that 2 hits the green line prediction somewhere like 66, somewhere, I don't know what the exact value of that is. If we go from 2 to 1.
I mean,
Yeah.
that's everything. Can you start where you
Yeah.
did that again, the first red dot?
Okay, the first,
Sorry.
no, that's fine. The first, so the green lines are our best fitting line, our prediction line. We've got a slope of this line, negative 2.55. So for a value of 2, the value of 2 hits our prediction line somewhere, I don't know exactly, it's something like 66. If we change and go from 2 to 1, that's a 1 unit change in x. So if we go from 2 to 1 on our x, that one hits the y, hits the green line here. Corresponds to value maybe 67 and decimal, I don't know, because it's not exact. When we go from 2 to 1, so from a value of x of 2 to a value of x of 1, and that's changing the x by 1 unit. Our y rose 2.55 or negative 2.55. The negative comes in if you go from 2 to 3, your y drops by 2.55. And the negative just shows you which way the line sloped. Is it going south, east to northwest? But this change in x of 1 yields, we go from 2 police cars to 1 police car, we can expect y, or the average speed, to go up by 2.55. If we go from 2 to 3, so 3 hits the green line here, and we go to 2, this is still a value of 1. This distance here is still 2.55, and if we go from 2 police cars to 3 police cars, we can expect speed to go down by 2.55. So we found the slope of this line, straight line. Questions about the slope?
I was just thinking, is that the same as the standard deviation?
No, it's just the angle of the line, how steep it is. So what we're doing with the regression equation, y equals a plus b or beta x. The y is our dependent variable, which is speed, equals a plus x is our independent variable, or number of police, and our beta is a negative 2.55. So if you have a positive and a negative, it's really just, it's now a minus. 2.55x. So y, or our dependent variable, equals a minus 2.55x. A is our y-intercept, or the value of y when x is 0, or where this line hits the y-axis. So when x is 0, what is y? That's your alpha. That's your y-intercept. So the only thing we're missing from the equation of this line, we've already got the slope, which is the most important part. Most important for interpretation, we'll see that in a second. Now we just need the y-intercept. What happens when x is 0?
Yeah, you know, in the book they put that 50 right on the. They don't put the 0 like you have it and then go up 50. They have it actually. I'm looking here.
Which page?
It's the next one over.
Return entry.
It just shows 50 as the.
But actually, there's a 0 there
18.3.
instead of the 50 being on the x-axis.
That's the y-axis scale.
That's
Yeah, that starts at 50 miles an hour.
the 0 is part of the numbers I know.
Yeah, 0 is part of the x.
It's
So
7,
there
6, 5.
was
Yeah, you
a
see how this is.
0.
Yeah, that's part of this axis.
Yeah,
Not
they
this.
should have done a little squiggle line
Okay.
to show that the y-axis starts at 50 and not a true
Okay.
0, but they did. This is how you can lie with graphs, too. If you were to run it from 0 to 75, the effect would look very minuscule, but once you change the scale. But yeah. So it's 0 for x, number of police cars. All right, let me erase the raw data. That's how we got our line. To find the y-interceptor A, the equation at the bottom of the page I gave you, A equals y bar, which is the y mean, minus your beta times x bar. And that will give you a, remember we've already calculated beta or b as a negative 2.55. That's the slope of that line. So the y-intercept, A equals the mean of y, which we had calculated it as 62. So 62 minus your beta, so minus a negative 2.55 times our x bar, or mean of x, which was 4. So that negative on that beta goes, this is going to be minus the beta. So that's why we got a minus the negative 2.55 times 4. That minus stays there, and then whatever your beta is, including the sign, goes into the beta. So what you get for your y-intercept, or this value here, though it's probably not drawn to scale, where that line hits the y-axis, A equals 62 minus, let's see, 2.55 times 4, minus a negative 10.2, which is the same as saying 62 plus 10.2. Minus negative. So your alpha ends up being 72.2, or your y-intercept. So even though it's probably not drawn to scale, this line hits the y-axis at 72.2. Therefore, now the equation of the line,
The line or the slope? Or they're the same?
the slope, the equation line has to have an intercept. The slope is just the angle, how steep it is.
Oh,
How's
okay,
that?
so
Yeah.
now it's hitting on there at 72 point. Okay.
Right. So we want to say y, our dependent variable, equals a or alpha plus beta or b x. So the equation of this line is y equals our alpha 72.2 plus our beta, which is a negative 2.55 x. And plus a negative, you can just get rid of that plus sign. So this line's equation is 72.2 minus 2.55x. Here's your B, here's your beta, here's your A, or your alpha, which is your y-intercept, and B is the slope. So B, negative 2.55 is how steep it is. That's the slope of it. And to get the perfect equation of that line, to get the exact equation of that line, you have to calculate the y-intercept when x equals 0. And so we calculate that as 72.2. And so that's the exact equation of that green line. Questions? This is what your regression computer will do. If it's a best fitting line through observed data, this is the best straight line that fit that data. And the equation in that line is y equals 72.2 minus 2.55x. Now the importance of it, I gave you room on page 6. What is the interpretation of the y-intercept and what is the interpretation of B or beta? B or beta is the most important one, so your beta or B is a negative 2.55, right? So how you interpret the slope or the beta, right? You can never go wrong if you use this template. You say, on average, ceteris paribus, which is I think Latin.
Is that habeas corpus?
I think it's Latin for all else equal, or holding all else constant. When we talk about regression, on average, ceteris paribus. What you have to say is a 1 unit increase in, I put in brackets for you to fill in, whatever your x is. A 1 unit increase in x leads to a put that in brackets because you have to fill this in. Beta unit and you have to determine also increase or decrease in whatever your y is. So the template we have in brackets will change based upon the information you're given. So always put in on average ceteris paribus a 1 unit increase in, we're going to figure out what x is, leads to a beta unit increase or decrease in whatever y is. So we came up with this equation, beta is a negative 2.55. You can put in, just put the number for beta. Some people get confused and you'll see why in a second. X, a 1 unit increase in x. What is x?
So would it be the same 1 unit increase or decrease in x? Because you can go in either direction.
Yes. Yeah, but it's, if you go decrease in x, then you've got to, it's easier to say increase in x, but yes, you can do decrease, but you may have to change the second.
Right.
Yeah,
So
you have to switch it around a bit, yeah.
yeah.
So x is what? 1 unit increase in what? What is x? What substantively is x? 1 unit increase in number of police leads to a whatever beta's number is. Don't worry about the sign yet. What is the number on beta minus the sign? Or not including the sign?
2.1. 2.5.
Okay. leads to a 2.55 unit. The sign tells you whether it's an increase or decrease. If it's a positive sign on there, it's an increase. If it's a negative on that beta, it's a decrease. So when you put in beta into your template, you just put the number in, and the sign tells you whether it's increase or decrease. In this case, the beta is negative. So a 2.55 unit decrease in whatever y is subsequently. Average speed of cars. And your regression, when you do it in SPSS, even though it's not part of your homework, it'll give you a beta for anytime you run a regression. And that beta, you can interpret it using this template. On average, ceteris paribus, or holding all else constant. That the holding all else constant becomes important with multivariate regression. When we controlling for, like with the weight example, exercise, gender, height, etc. In this case, we've just got one independent variable, but still put it in there. So on average, ceteris paribus, and 1 unit increase in the number of police leads to a 2.55 unit decrease in the average speed of cars. So essentially this is saying each additional police car you add to the street decreases speeds on average by 2.55 miles per hour per police car. So when you go from 0 police cars to 1 police car, speed will decrease on average 2.55 miles per hour. When you go from 1 police cars to 2 police cars, another 2.55 decrease in speed. 2 to 3 police cars, another average decrease of the speed of cars on the freeway by 2.55 miles an hour. And it's an average, it's not an exact, it's our best prediction because we have observed data in blue. We put a best fitting line through that data and came up with the equation of that line. It's not going to be, in every case, when you go from 3 to 4 police in a car, in every instance that you do that, the cars are going to decrease in speed by 2.5 miles per hour. Some days it may decrease by 4, some days it may not decrease at all, but on average, the effect of going for an additional police car, adding an additional police car is a decrease of 2.55 miles per hour. Questions? The last thing to interpret on there for the night is the y-intercept of 72.2. Beta is the most important because it's telling you the effect of x on y, or the number of police cars on speed. The y-intercept, you will always get a y-intercept. Sometimes it makes sense, other times it doesn't. And so we don't spend a lot of time on the y-intercept. It's mainly beta. Beta shows the effect. But if you want to interpret the y-intercept, the interpretation of the y-intercept is when x, whatever x, is 0, whatever y is your value of a or alpha, or your y-intercept. So the template for that, for y-intercept, when you set x to 0, or when all of your x's, when all the x's are set to 0, y is whatever that value of a is. So when all of our x's are set to 0, in this case we only have one x, one independent variable, which is number of police cars. When number of police cars is 0, or there's no police out on the street, y, or the average speed of cars, is, our best guess is 72.2 miles per hour. So when x is 0, where does that line hit the y-axis? It's 72.2. When x is 0, what is absent? Well, we're measuring number of police cars, so number of police cars is 0. we can guess the average speed. Our best guess is going to be 72.2 miles an hour. The y-intercept, to kind of conclude, and why it's not as important as the beta. The beta will give you the independent effect of x on y. You will always get a y-intercept, okay, because the computer is going to put a best fitting line through the data. So if we have weight, let's do as a function of height. Tend to be, on average, the taller you are, the more you weigh. You're going to have data sprayed out across society. These all represent points for weights based upon heights. It's probably something like that. The computer's going to put a best fitting line through this data. Something like that. It's not a perfect way to show it, but let me fudge it a little bit. Okay. 0 inches and 0 weight. Let's say this is 250 pounds. I don't know. Okay. This graph will have a positive slope. Its beta or b will be positive and some number. The computer will always put a line through it and will always have a y-intercept. Okay. So when x is 0 or when height is 0, the computer says somebody still weighs something. That doesn't make any substantive sense. So sometimes your y-intercept will make substantive sense, like, yes, it is possible to have 0 police cars on the street. It's very much possible that that situation could happen. But it's not possible to have a situation where an individual in society has no height. You will get a y-intercept. Somebody that doesn't have any height will weigh, I don't know what that number is, maybe it's 5 pounds. But that's just because the computer has to put a best fitting line, there has to be a y-intercept. In this case, x being 0 is not possible. Y-intercept, you wouldn't interpret it, it makes no sense. It's just there to finish the equation off. So that's why we focus on the beta, because that's the independent effect of x on y. All right, questions? Stop recording.